Now we're ready to start Chapter 8. And Chapter 8 will sound like a familiar topic, working with the binomial distribution or binomial probability. And so let's start with the first example, and this will give you a little refresher of FS. So you roll a die 4 times, and you count the number of sixes that come up. And you want to find the probability for a certain number of sixes in 4 rolls. So you roll a die 4 times, and you're interested in sixes. And we want the probability distribution for the number of sixes that will come up in 4 rolls. So we know that our probability distribution is going to look something like this. That we know we can get no sixes, 1 6, 2 sixes, 3 sixes, and 4 sixes, etc. And remember what we do for this. So let's look at the multiplication counting idea, and let's say, for instance, I want to figure out the probability for this specific value. So I know if I'm going to get 1 6, let's say the 6 is occurring here, and I have a 1 out of 6 chance of that happening. Then this would be a non-6, and another non-6, and another non-6. And I have a 5 6 chance of that occurring in each of these values. So we could get fooled and think that that's what the probability is of rolling 1 6. This is actually the probability of rolling 1 6 in 4 rolls if we want the first one to be a 6 and the other 3 are non-6s. And we could actually have the 6 occur here, or it could occur here, or here, or here. So if I look at my setting, again, here's my 6 happening. And then I have the 3 non-6s after it. And if I only do this much, then I'm finding the probability of specifically having the first position have a 6. And there are 4 different ways for that to take place. So likewise, I found the same probability for each of the other occurrences. And let's look at this one. Let's say I had 2 6s. And notice that we'll review what the formula is in a second, but let's look at the theory behind it of what we're doing. Once again, if I have these 4 slots, and I know that I want to have 2 6s, I could assume, let's say this one is a 6, and this one is a 6, and then these are the 2 non-6s. So I would have 1 6 times 1 6 times 5 6 times 5 6. And so far, that's what we would think our probability is. However, that's not correct because we know that there are lots of different positions in which we can place down the 2 6s. And let's look at where this 6, there actually are 6 ways, and let's look at those ways. And I'm going to count. I could put them in these 2 positions, or these 2, or these 2, or these 2, or these 2, or these 2. So if I count, here's 1, 2, 3, 4, 5, 6. So I have 6 different places that I can place those values down. So I did my calculations of all of these different events in my probability distribution and found the corresponding probabilities. I know if I add up all these values that they'll add up to 1 because it always does in a probability distribution. And this would actually be the binomial setting. Now let's review what it means to have binomial probability. And there basically are 4 characteristics that take place. First of all, the bi we know means 2, so we would have each observation has to fall into one of 2 categories. So you either have a success or a failure. Up here, we had that you either rolled a 6 or you didn't roll a 6. We could have that it rains, it doesn't rain. Somebody makes a shot, they miss a shot. So we can always have 2 different categories in which the items have to fall. Now, secondly, there has to be a fixed number of observations that we're looking at. In our case, in this die rolling question, we were rolling the die a fixed number of times, 4 times. Another characteristic of binomial is you have to have independence between each of your observations. Each time up here when we roll the die in the 4 die roll, we would have to have independence between each roll. And we have the probability of that die coming up 1 6 being the same each time. So those are the characteristics we need for a binomial setting. Now, here's a second question we're going to look at and see, do we have the binomial setting in this case? So you observe the sex or the gender of the next 20 children who are born at a local hospital. So you have a fixed number of children, and now we're going to let X stand for the number of girls that you find. So the question is, do we have the setting? And we would have either you have a boy or a girl. We would have, for each of the children who we would look at, we have a fixed number of children, 20. If we don't have identical twins, then we would have independence between each child that we would look at, and we would have the likelihood of a girl being 1/2 each time. And we could actually write the probability distribution of how many girls we would have. We could have as few as 0. We could have 1 girl out of 20, 2 girls out of 20, and so on, all the way up to 20 girls out of 20. And naturally, a lot of those are not going to be very probable. It's very improbable that we would look at the birth of 20 children and have none of them be girls. But you don't necessarily have half of them be girls. So let's look at another question. A couple decides to continue to have children until their first girl is born. And then once they have a girl, they're going to stop. X is the random variable of the number of children that the couple has to have in order to finally get that first girl. Now, once again, notice you're either going to have a girl or a boy. But here's the problem. You don't know how many children you're going to have. You're going to continue to have children each time until you finally have the girl. However, look, the number of observations from one child to the next actually would have independence. And the probability of a girl would stay the same each time. But that idea that you don't have a fixed number of trials is going to cause that situation not to be binomial. Now, remember that binomial probability is very predictable. And so remember that if we had a normal distribution, we used a notation of a normal distribution, and you have a particular mean and a particular standard deviation. So if you saw this located someplace, you go, oh, I'm talking about a normal distribution. Just like if we see this notation, that would mean we have a particular binomial probability distribution. And in our case, a binomial distribution has 2 characteristics that we need to know. We need to know how many observations are you going to look at for like a trial. So we had 4 dice, 4 rolls of a die, and you had 20 children being looked at being born up here. And we need to know what the probability of a success is. For our situation here, our probability of a success was you're rolling 6 was a success, and that was 1/6. Here, the probability of a girl being born was our, quote, success when we were looking at the number of girls being born, and that would be 1/2. And then this is our setup for recalling how we find the particular probability of a binomial event. And so let me equate this to just another example, and then we'll look at the characteristics we have here. Okay, so let's say we had a situation in which we were going to have somebody shooting baskets. And let's say that the probability that someone makes a basket is an individual shot is 0.7. And let's say we are going to have that person shoot 10 shots. Now, let's say I ask, what is the probability that this person goes up to the basket, shoots 10 shots, and I want to know what's the likelihood that this person makes exactly 7. Now, theoretically, let's think about that. We're going to have them shoot 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And let's say, just for purposes of this, we're going to check, first of all, to see if this is a binomial setting. First characteristic, you either have to have a make or a miss. Secondly, we have specifically 10 shots being shot. Third, we're going to make the assumption here that each shot is independent. And then fourth, we're going to have the probability of making the shot be a 70% chance each time. Now, if we want to find the probability that a person is going to make 7 out of the 10, let's just say 1, 2, 3, 4, 5, 6, 7. Let's say these are the ones that are being made. So we would say each of these would be a 0.7, 0.7, 0.7, or a 70% chance that each of those would be made. And we'd have a whole series of 0.7s that we'd have to multiply together. And now, this one would have to be a miss, miss, miss. And the likelihood of a miss is 0.3, and we would have 3 of those. Now, if I multiply that out and give that answer, that can't be the appropriate value due to the fact that I have lots of ways that I can make 7 shots out of 10. I could miss the first 3 and make the last 7. I could miss this first one, miss these last 2, and make everything else. So there are a whole bunch of different ways to have that happening. And think of this combination that, if you remember from binomial probability, where it comes from. I have 10, if I think my fingers, I have 10 different shots that we're going to look at. And we want to choose 7 of those to be made. And so that's where that combination comes in. That combination of, I have 10 shots and I'm going to choose 7 of them to be made, that combination actually counts all the different ways that I can pick 7 of these. And the order doesn't really matter in which I pick these. If I say, hey, I'm going to make this one, this one, this one, this one, this one, this one, this one. No, I'm going to make this one, this one, this one, this one, this one, this one, this one. It doesn't matter the order in which I choose these. So this is a combination of, there are 10 things, and I'm going to pick 7, and it doesn't matter the order. Now, this notation is probably new to you. This is another way to write the combination of n choose k. Just different textbooks, different resources will have different ways of showing that. And so that's a common way of seeing the combination notation. Your calculator naturally has this combination notation. As you usually call it an NCR button because it's an N, C, and then it's usually an R on your calculator. But in general, look at what I did here when I found this probability. We're going to generalize it. Here is the probability of success. Here is the probability of a failure. We want k successes. You actually will have k of these successes multiplied out in some type of a sequential order. Then you're going to have n minus k failures. So this is how many successes you'll have. This is how many failures. Notice that the sum of these two will always add up to n, just like the sum of these added up to 10 shots. Now, if we only did that, we're specifically having the successes happen at the beginning and the failures happening at the end. And we don't have in the wording that they have to happen in a particular order. So we need this combination to pick all the different ways that we can have all of these k successes happen somewhere in those n trials. Now, what is a combination? Remember, the combination is these two notations, is really the n factorial divided by the difference factorial divided by the k factorial. So that's where the combination comes from. And remember, that picks, you have n things to choose from, and you're picking groups of k where the order doesn't matter. And once you pick an item, you aren't going to have replacements. So I can't say, hey, I'm going to have this one be the made shot. I can't say I have this one be the made shot, and then the next time say, hey, I have this one be the made shot. Because once I pick this one, I can't pick it again as a position. All right, so let's turn the page and look at a couple examples. And we'll get to the calculator usage in a second, but let's look at number 3. So we have a factory employs several thousand workers, of whom 30% are Hispanic. This happens to be one of the questions that's in your textbook. And they have 15 members of a union committee are going to be chosen from the workers at random. And we want to predict the number of Hispanics who will be on the committee. And so the first thing we need to do is check to see, why can we actually simulate some probability answers with a binomial distribution? And if we have, think of this as kind of a pool of several thousand people. And we know of these that 30% of these people are Hispanic. And we're going to pick 15 people, and these would be like all mixed up. So you can almost think of it like marbles, that you have a whole bunch of several thousand marbles in a big, huge vat, and of which 30% are a certain color. and we could say those colors represent picking a Hispanic person. And so we're going to pick 15 people. And the question is, if I do this probability, and maybe I want to know what's the probability that 5 of these people happen to be Hispanic out of the 15, or 2 of the people happen to be Hispanic out of 15. And this setup would be binomial because we either have, when we pick a person, it's either going to be a Hispanic person or not. We actually know the likelihood is going to be a 30% basically each time because we have such a large number of people. When I'm only picking 15 people out, the probability of Hispanic is basically the same thing every time. Have a 30% chance of Hispanic and about a 70% chance of not Hispanic. If we randomly pick people, they would vary independence between trials, and we're picking specifically 15 people. Now, if I ask what's the probability that exactly 3 members on the committee are Hispanic, when I pull these 15 people out, I'm thinking, okay, well, how many of those people are Hispanic, and what's the chance that exactly 3 of them? So 12 of them are non, and 3 of them are. So here's my random variable, x being the number of Hispanics being chosen. Sorry about this blue here. And here's the probability of a Hispanic person being chosen. Here's the probability of a non-Hispanic. My exponent, how many of those people do I want to be Hispanic? 3, which means 12 are non. So these two will always add up to how many you're picking. Now, if I only do that, I'm finding the probability basically that the first 3 are Hispanic and the last 12 are not Hispanic. But I want there to be the possibility that the first one's Hispanic, a whole bunch of non, and like the last 2. So there are lots of different ways to pick 3 out of the 15 to be Hispanic, and this combination does it for me. And so you need to be able to write this notation down. Now let's review. Well, actually not review. You didn't learn this in FS. But if I'm going to do the calculation, remember that the probability button, we do have this NCR button. And so that's under the math and probability. So I could take 15, math, probability, this NCR button, choose 3. So there actually are 455 ways to pick 3 people out of 15 to be a specific position for where the Hispanic person is. And then I could multiply that by 0.3 to the 3rd power times 0.7 to the 12th power. And now I have my probability. Now we actually do have a feature on the calculator that is very nice. And the feature is, and let's go back up to the top. The feature on your calculator is called a binomial PDF. It's really the binomial probability density function. However, what we will want to think of it as is this is a binomial probability where it's going to tell me a particular P for particular binomial probability answer. And if we go to second and distribution and arrow down, and you want the PDF. And the binomial PDF button is set up that I tell the calculator how many trials. I'm going to have 15 Hispanics being chosen. The probability of a Hispanic being chosen is 0.3. And then X will stand for how many successes I want. And in our case, we wanted 3 successes for Part B. We wanted 3. Whoops, need a comma in there. And then when I hit enter, notice this answer is exactly the same as that because the calculator has been programmed to do that calculation right here. So the calculator, when we put the values in for how many trials, probability of success, and the number of successes here, that will actually do the calculation for that binomial situation. Now, on your tests and your AP tests, this is not a sufficient answer for any type of probability question, although it's nice to type in, and I might even type this in rather than key punch all these steps in. This is required on the AP exam to write out something like this, or I could put this as the corresponding combination of 15, choose 3 right here. But you must write this type of notation out. You can't just put the calculator feature answers down. You have to show where it came from. Now, let's look at the next question. Here we have the question, what is the probability that 3 or fewer Hispanics are being picked? And 3 or fewer means I would like to have, if I think of the entire probability distribution for how many Hispanics could be picked, X standing for the number of Hispanics being picked, we know none could be picked out of the 15. 1 could be picked out of the 15. 2, 3. We actually figured that answer out. We know that from right here. We could have 4, all the way up to all 15 could be Hispanic. Now again, that's very, very unlikely to happen, but it could happen. So now we need to figure out what is the probability that 3 or fewer Hispanics are being chosen. So we really want these answers to be added together. And so I wrote it out in the whole notation with the symbolism, that's the correct symbolism, that this is what I want. Now these are the probabilities that I want to add up. Here is the likelihood that I have no Hispanics, and I have 15 non-Hispanics. Here's the probability that I have 1 Hispanic being chosen, and then 14 non, and so on. Now that does get tedious to do that entire computation, so we will have a shortcut that I'll show you in a second. But it is not sufficient to write down calculator notation for this. You need to be able to either write this down, or we actually have a faster way by using some sigma notation. And let me show you the sigma notation. The sigma notation, if we look at what's happening, I can see that each time each of these different features has a combination, a probability of success, and a probability of failure. And they're each raised to an exponent that's changing, as well as this combination has this number changing. So my first term had this be a 0, 0, and this was a 15. My second term has this being a 1, this being a 1, and this being a 14. And so see how this rule that I've written down is actually, as I let I go from 0 up to 3, and this sigma means I'd be summing up all of these terms. This notation of sigma notation is actually showing me the sum of all of my terms here in a nice little confined setting. Now for our tests and the AP test, you need to be able to write either this or the sigma notation. I highly recommend you be able to write both. Now, again, this is tedious to do all those calculations, but one nice thing is we do have another feature on our calculator that is called the binomial CDF, and that's referred to up here. And so let's go back and slide up here a second. So the binomial CDF button, you want to think of it as technically the binomial cumulative distribution function. But what you want to think of is the binomial PDF is to find a particular number of successes, as opposed to the binomial CDF is going to cumulate or accumulate a number of probabilities. And it basically is input similarly, and you have to be careful which button you're using. You put in the number of trials, you put in the probability of success, and then you put in the number of successes that you want your value to be less than or equal to. So it will add up all of those values in the probability distribution from 0 up to whatever you put here. So let's go back down. So this is the notation that I would enter to add up all of these different events. I hit the binomial CDF, and let me put this here. So again, it's under the same place. We go to second in distribution. Under binomial CDF, I type in 15, comma, 0.3, comma, and 3. And see, I'm actually doing almost the same key sequence, except this was a PDF and this is a CDF. And this one is going to accumulate or cumulate from 3 down. We have no button to accumulate upward. It's always from this number of successes down. And when I do that, I get this value. Now, if I wanted to find the probability of having 5 or more Hispanics on my committee, again, let me flip my little table around. Notice I really would be wanting to find all of these. Now, if I had my whole probability distribution written out, I could add those up. Now, I don't want to write all those down in this type of sequential way here, because I'm going to have to be writing down a lot of different possibilities, actually 11, because the difference plus 1. Difference here is 10 plus 1. So the number of categories you'd be adding up is actually 11. So I definitely want to be able to write that in sigma notation. And watch how easy it is. There's my sigma notation for it. My sigma notation says, you know you're going to have a combination. You know you're going to have a probability of success, a probability of a failure. Whatever you're going to have for that combination choosing is going to match this. This is how many successes, and this is how many failures you're going to have. And as this number increases, and this actually drops down. However, this time I want to start by plugging 5 in, and then I'll plug in 6, and 7, and 8, and so on until I get to 15. So this is my nice shortcut way of writing it down. Very efficient, nice, but I don't really want to find all those 11 events and add them up. So I definitely want to use my binomial CDF button. But if I look back at my table, remember, I want to add up 5 up to 15. And notice I can't add upward. I have to add downward. So I really want to find these from 4 down. And if I find the probability from 4 downward, the complement will be 5 up. And so that's the way I'd actually be placing it into my binomial CDF. And that's what my answer would be. Now, we're going to skip the simulation and we're going to go right over here to this part. And we're going to look at how do you find the mean and standard deviation of a binomial probability distribution. And there is a shortcut. Naturally, we know how to find the mean and standard deviation of a binomial of any type of probability distribution. If I have this is x and this is the probability of x, and I have this is 0, 1, 2, say for the Hispanic setting, all the way up to 15, I know I can find the probability of each of these, which means I can take and find the mean by multiplying each of the components of the random variable times its corresponding probability, and I can add all those up from the first one, and let's say I call it sub-0, from the first one to the last one, and I can actually figure out what the mean is. And I can go back and determine the standard deviation, because remember the standard deviation for a random variable was I would take each one of my random variable elements minus the mean squared, multiply by its corresponding probability, and then I would add all of those products up and square root naturally to get the standard deviation instead of the variance. But there is a shortcut, and it's very easy to find the mean and standard deviation for a binomial setting. It's not cumbersome, and it's set up like so. The mean is as simple as multiplying how many you have times the probability of a success. So if we look down here, if we were going to pick 15 people at random, and we wanted to know what the expected number or mean number of Hispanics is, it's as simple as 15 times 0.3. So we'd expect if you continue to pull 15 people out, count how many Hispanics there are, write it down. Pull out another group of 15 people, write how many Hispanics are in your group of 15 and write it down, and do that over and over again. We would expect that number on the average to be 4.5. Now, secondly, we need to be able to find the standard deviation. We really don't want to make these entire probability distributions and do it longhand. We want the shortcut. And the shortcut is to take n times p, so how many elements times the probability of success, which in effect is actually the mean, this part is, times the probability of a failure. That's what 1 minus p stands for. So this is really how many are you choosing, probability of success, probability of a failure, multiply those together, and if you do that, that's the variance. And then when we square root it, we get the standard deviation. So we could do that in this setting. If I find the standard deviation for the number of Hispanics, very simple. So again, if I pick 15 people, count how many Hispanics, write it down. Pick 15 people, count how many Hispanics, and write it down. And do that over and over again. Those number of Hispanics that I chose are going to vary like this. Now I think I'm going to stop the video at this point, and we have a couple more things to do, but I think I'm ready for you to start to work.